Okay, so it is currently 5:01. We will get started. So, first of all, welcome to our third class meeting. Um, so first of all, just a quick reminder, the homework is due um, on Saturday. So we will, if you have any questions about the homework when you do it, you can ask me in class then. Otherwise, if you have any questions before then, you can, of course, shoot me an email or post on Google Classroom. Okay, so without further ado, I will share my screen and we will get started. Yeah, okay. So, and of course, once again, if you at any point you have any questions, you can unmute yourself. I won't really be checking the private chats, so definitely feel free to speak out if you have any questions throughout the lesson. Okay. So today's topic will be continuity. And this is just like limits. So the previous topic, this is going to be very important. This is going to be a very important foundation for calculus, and we will use this concept of continuity a lot in later in this course. Yeah, so this is a really important topic today that we're covering. So, kind of get an introduction to continuity. Suppose we have a particle, and this particle is basically sliding along a curve, right? So I can replay that animation. So here's the particle, and think of the curve as, I don't know, a roller coaster track or something like that, and the particle is just smoothly gliding along the roller coaster track. Now think about what happens if we slightly change the curve. So most of the curve is still the same, except now at x equals -1, instead of being defined as 1, the function is defined as 2. What happens if the particle tries to slide down this curve now? Well, it can start over here, but then eventually it will get to x equals -1. And at x equals -1, notice this particle will fall out, right? It will fall out of its trajectory because there's this hole in the graph. And so the main difference here is that in one scenario, the particle does not fall off the graph, and in the other, it does. And this is because there is a hole. The function doesn't behave as it normally would have at x equals -1. And so we say that this red function is continuous at x equals -1. And the blue function is discontinuous at x equals -1. It doesn't really behave normally like it should. Okay. So another way of thinking about continuity is smoothness. Really, continuity is a measure of how smooth the function is. So notice at x equals -1, this function is a nice smooth curve. Really, no interruptions, no holes, no anything. But here, this function is not smooth. And notice that this is because we have a hole right here, and this causes the function to behave differently from how it would if there had not been this hole. And so the fact that this function is not smooth makes it discontinuous at x equals -1. Okay. So a couple of things about this new topic of continuity before we keep going. So continuous is the same thing as saying smooth. If the function is continuous at a point, that means that it is smooth at the point. There's no interruptions in its flow at that point. When we don't specify a point at which the function is continuous, we assume that it's continuous for all real numbers. So we can say that a function is continuous, like y equals x, f of x equals x, right? That is just a line, that is continuous, that is always smooth. And when we say that a function is continuous, we assume that we're talking about for x over all real numbers. When a function is not continuous at a point, we say that there is a discontinuity at that point. So for instance, in the previous example with the red function and the blue function had a discontinuity at x equals -1. And then a function may be discontinuous at a point, even if it is defined at that point. So what am I talking about here? Well, if we go back to this slide right here, notice that this blue function is discontinuous, even though it is defined at x equals 1. It's defined at x equals 2 as f of x equals 2. And yet it is still discontinuous. So this scenario could happen. Just because a function is defined at a point, that does not mean that it's continuous there. Okay, so let me just go back to the slide. Then, on the other hand, if a function is undefined at a point, there is no way for it to be continuous at that point because, well, we can't really work with that function at the point anymore, much less with some of its properties at that point. So these are kind of the four major things that you need to know about continuity before we dive deeper into the subject. So if you have any questions about any of this, you should ask me now. No questions? Okay. So when is a function not continuous? Well, one scenario could be what if there is an asymptote. So we talked about asymptotes a bit in the previous class. An asymptote is a line, whether vertical or horizontal, that the function approaches, but doesn't quite get close to. So it approaches that line, but it doesn't cross it. And in this case, we have a vertical asymptote, like this. So we can see that this function is shooting off toward infinity as x gets closer and closer to 0. However, it won't actually ever cross into x equals 0. And because of this, this function is undefined at x equals 0. And of course, as we already talked about, if a function is undefined at a point, it can't be continuous there. Another example is a hole. So in this case, this function isn't defined at x equals 0, but there is no asymptote. It's just like a single point at which the function is undefined. And this essentially means that even though there is no asymptote, this function is still not continuous because it's undefined. So the function could still be defined, but not be continuous. For instance, this function right here, it's defined at x equals 0 as 0. So we say f of x, so f of 0 equals 0, but then it suddenly jumps to this branch of the curve. And because of that, even though it's defined, it is still not continuous. And this we call a jump discontinuity because there's a gap between these two branches of the curve. Similarly, it could be discontinuous at a point. So there could be a hole, the function suddenly doesn't behave as it normally would, and is defined at some other value. And so this is what we call a point discontinuity, or a removable discontinuity, because it's only at one point we can essentially remove it. So it's defined, but discontinuous. So these are the four major types of discontinuities that you will need to know: asymptotic, a hole discontinuity, a jump discontinuity, or a point discontinuity. So those are the four major types. Okay. So one question we can answer with that relates to discontinuity and continuity is, well, is f of x equals 1 over x continuous? And then the question asks, if not, what type of discontinuity does it have, and at what input? Now notice that the function has a vertical asymptote at x equals 0. So if we graph this function, we can quickly see that it approaches a vertical line, but doesn't quite cross it. And it's undefined at this point, and because of that, of course, it's discontinuous at that point. So then another question is, f of x equals x squared continuous? And once again, when we say continuous, we mean continuous for all real numbers. We could say continuous at, I don't know, x equals 1, but when we say continuous without anything, we assume that it means continuous for all real numbers. So the answer is yes, it is continuous for all real x because it's just a smooth parabola. If you think about it, right, there's no interruptions to the flow of a parabola. It's basically a smooth U-shaped curve. And because of this, it is continuous for all real numbers. Okay. So any questions so far? Nothing in the chat? No? Okay. So if there's no questions, we will go on to some practice problems that relate to this topic. So suppose we have this function, f of x equals 1 minus cosine of x over x. And the question is this continuous for all real numbers? And if not, what type of discontinuity does it have and at what point? So I will give you about 2 minutes or however much time you want, maybe 2 to 5 minutes to solve this problem. And when you're done, maybe you can write to me in the chat what your solution is. Okay. Okay. So there are some answers coming in the chat, so I don't want to, view those answers while I'm sharing the screen with you guys. So I'm going to take the problem statement off the board, and I'm going to be replying to some of the chat comments.
You could just pause your screen sharing.
Wait, would you be able to see the screen if I did that, or would I not be?
I think so.
Yeah.
But then the screen wouldn't move, and once you unpause it, then you would everybody would be able to see you moving your arrow around, and the chat would appear.
Okay, that's actually, I didn't know that. Thanks so much for letting me know. Okay, so I will actually do that. I will pause share. Thanks so much. I actually didn't know that I could do that. Thanks. Okay. Okay. So I will go over the solution now. I'm gonna unpause my sharing. Okay. So I hope you had a chance to think over this problem. The answer is no, undefined. So notice that when we plug x equals 0 into the function, we get 1 minus cosine of 0, which is 1 minus 1, which is 0. And then we divide that by 0. So at x equals 0, this behaves really weirdly. So it's definitely not defined at x equals 0. So it's not continuous, definitely. And it also doesn't have an asymptote. And this is because we know that when an asymptote occurs, that is because when we plug some value into the function, we get a non-zero constant over 0. But here we got 0 over 0, and 0 is not a non-zero constant. And because of that, we know that there can't be an asymptote at x equals 0, which means that the only other alternative is a whole. Once again, this is the only other alternative because this is the only other type of discontinuity where the function is undefined. Okay, so one last problem before we go on. By the way, did anyone have any questions about the previous one? No? Okay. So now the problem asks, is the absolute value of x over x continuous? And if not, what type of discontinuity does it have and at what point? So I'll also give you about 3 minutes to think about this. And this one is actually really interesting problem. Okay, so is absolute value of x over x continuous? And as usual, please type your answers in the chat. Thank you. Okay. Okay. So I will resume share screening and we will go over this problem together. So this problem was a bit more tricky because the answer is quite unexpected. So this is actually the graph of this function, absolute value of x over x. And one way we could have come up with this is notice that when x is a positive integer, absolute value of x is positive, x is positive. In that case, the two are equal. And for all positive numbers, the function is equal to 1. So we have this horizontal line here. And then similarly for negative numbers, absolute value of x is still positive, but x is negative. And so overall, you have negative 1. So for positive numbers, it's 1. And for negative numbers, it's negative 1. And then at 0, right, if you plug in x equals 0 here, you get 0 over 0. And so in this case, we know that it's definitely not defined. It's definitely not continuous. But we notice that there's a jump between this negative branch and this positive branch that occurs at x equals 0. So it goes from being -1 to undefined at a single point to to 1. And you can also say that there's a hold here because it's undefined at a single point. So here there's both a jump and you could say a hold discontinuity. Okay. So all this time we've been talking about continuity as a measure of smoothness, but smoothness is a very qualitative adjective. It's not, well, it's not rigorous. It's not mathematically like something that you could write on a test, like this function is smooth, and you wouldn't receive credit for that. So how would you define continuity using math? Well, here is where the previous class about limits comes in. Because a function is continuous at x equals a, if and only if the limit as x approaches a of f of x exists and is equal to f of a. Okay, so let's piece together this this definition. So what this is saying is, so suppose we have a function, and suppose we have, well, some sort of ordered pair a comma f of a, right? And notice that in this case, the limit as x approaches this value right here, this blue value right here, it exists, and it's also equal to the value of the function. So this provision that the limit exists, this accounts for when the limit could be infinite, or where the left-hand limit or the right-hand limit could be different from each other. And in this case, the function would be undefined at that point, and we won't even be talking about continuity. So that is this part right here is to make sure that the function is defined, and then the limit equaling the actual function, this is to make sure that there's no point discontinuity. Because, for instance, the function could have been defined at this point right here, but then it wouldn't have been continuous. There would have been a hold here, and it would have been defined somewhere different. And so we have to make sure that this limit where it would have been defined is equal to the place where it's actually defined. And this if and only if here, this means that a function is continuous if this limit definition is true. And we also know that if this limit definition is true, then the function is continuous. So it's kind of like a two-way relationship between the function being continuous and this limit definition. And so notice that this also explains why a lot of the functions that we talked about when we were talking about limits could be evaluated with direct substitution. Because if the limit as x approaches a of f of x exists and is equal to f of a, well, then we can just plug in x equals a into this thing right here, and we would get f of a. So the limits that we can evaluate with direct substitutions are the limits of continuous functions, or maybe not functions that are continuous everywhere, but at least functions that are continuous at the point where we want to evaluate the limit. So this is how a mathematician would formally talk about continuity using limits. So why do each of these discontinuities that we talked about, why do each of the 4 discontinuities fail to pass this this definition? So notice that in a jump discontinuity, like we were talking about with the absolute value curve, right? The limit doesn't exist because the left-hand limit and right-hand limit, as the function approaches the point where the discontinuity happens, they aren't equal. There's a slight jump. And because of this, there is no limit, right? The limit as x approaches a of f of x doesn't exist. And because of this, we know that the function is discontinuous because the limit actually has to exist. Point discontinuity is a discontinuity. It's not continuous because the limit exists, but it isn't equal to the actual value of the function. In asymptotic discontinuity, the limit simply doesn't exist because it is infinite. So the function shoots off to infinity, or negative infinity, or one tail shoots up to infinity, the other to negative infinity, and in all 3 of those cases, the limit doesn't exist. And then a hold discontinuity, the limit exists, right? The function definitely approaches something finite as x gets closer and closer to that point. But the thing is that at that point, the function is undefined. And because of that, it can't be continuous there. So this is why all of these 4 things right here are actually discontinuities. And it also serves as a verification that our definition actually works. Okay. So now we will talk about something that is called the intermediate value theorem. And the intermediate value theorem is a very useful application of continuity, and we will be using it in this calculus course. So this is definitely something important that you need to know. So theorem states that if a function is continuous on the closed interval from a to b, then the function will take on any value between f of a and f of b. So what does this mean? Well, suppose we have this continuous function. So it doesn't have to be continuous everywhere, just on the closed interval between a and b. So this is basically all the numbers between a and b, including the actual numbers a and b. And so notice that the function takes on all of the values between this line and this line. And this is once again because the function is continuous. So if we tried, for instance, not to take on the value f of x equals 2, if we try to avoid crossing over this line, right? Because as soon as we cross over this line, we will actually have passed through x equals 2. So suppose we are trying to avoid that value, then we would have to, like, it would be impossible for a continuous function to cross this thing right here, well, without actually being equal to it. So the fact that this function is continuous is really really helps us to make sure that the function passes through all the points between a comma f of a and b comma f of b. Notice that it doesn't say anything about these points right here. So the function could pass through these points. It doesn't have to. It could have passed a bit lower, but the whole point is that all the points on this part of the curve, yes? Okay. Yeah, just please make sure to use the chat. Like, you know, don't use the chat while I'm giving a lecture if I don't ask you to, please. Okay, thank you. So what was I going to say? Yeah. The most important thing is that this function passes through all the values between f of a and f of b. This thing actually has some pretty useful applications. So how do the police catch you speeding? Well, they actually use the intermediate value theorem. So this isn't like a hypothetical setup where they would have been using it. They actually use this method in real life. So the police typically have a special camera, and they can use it to find your speed. So they can photograph your car, and they use like some sort of artificial intelligence to figure out that your speed, when you enter a speed limit area, suppose it was 30 miles per hour. And then when you leave the speed limit area, they again take the photo of your car with their special camera, and they find that your speed was 70 miles per hour, for example. And then we notice that since the time versus speed function is continuous, you must have driven at every speed in between 30 miles per hour and 70 miles per hour. And this is, once again, by the intermediate value theorem. So firstly, the time versus speed function is continuous because no vehicle has yet been developed where you could go from one speed to the next discontinuously. If you want to go from one speed to the next, you have to go through every single speed between those two speeds. You can't like suddenly start from rest and suddenly accelerate to 60 miles per hour in 0 seconds. That is impossible. And because of that, this time versus speed function is continuous. There are no discontinuities. And you also must have driven at every speed in between 30 miles per hour and 70 miles per hour because those were your starting and end points, right? This is once again by the intermediate value theorem. And then the speed limit 60 miles per hour, then you're in trouble because the police know that since you drove in between 30 miles per hour and 70 miles per hour, and you hit every single value between those 2 points, you also hit 65 miles per hour, which is above the speed limit. And so because of that, you're in trouble. You have been caught speeding. So once again, if the speed limit was 71 miles per hour, the police can't use this method because you might have driven at 71 miles per hour before slowing down and returning to 70 miles per hour, but you might have not. You don't have to. But you do have to cover everything from 30 to 70. And so if the speed limit is anywhere between then you're in trouble. Okay. So here's a recap. This is about class is going to be about over pretty soon. So once again, continuity is the measure of the smoothness of a function. Once again, this is a very informal definition, but this is essentially what continuity is. And a function is not continuous when the smoothness breaks, when there's a jump, a hole, an asymptote, or a point discontinuity. And a function is continuous at an input if and only if the limit of that function as x approaches that input exists and is equal to the value of the function at that input. So this may seem like a mouthful at first, but just think about the fact that the value that the function approaches at an input has to be equal to the value of the function at that input in order for the function to be continuous at that input. Then continuity has many applications, such as the intermediate value theorem. Okay. So this is it for our presentation. Does anyone have any questions about anything we did? Like anything at all? Okay. So once again, this is a very, very important topic that we will definitely be using a lot in this course. Yeah, so a lot of the derivative stuff and integral stuff that we will do later on will heavily rely on this topic of continuity. Okay. Any questions about the homework if you want to talk about them now? Or send me a, yes.
So for the homework questions, since it's due next class, will you be taking up the homework questions next class or not?
No, I will try to review some of the homework questions and answer some of your questions on the homework next class. Yeah.
Okay, no problem. Also, I'm busy next class, so I won't be able to attend. Sorry about that. So yeah. Just a heads up.
It's fine. I will post a recording of the class on Classroom. Yeah.
Okay, no problem. Thank you.
Okay. And by the way, more about homework. So I will post homework problems for the class probably before 6. I might not be able to post it before 6, but I will try to get around to posting it before 6. These problems will be very similar to the other problems that we covered. Just because, well, a lot of the stuff is pretty similar. But yeah, this class was a bit short because, well, the idea is kind of intuitive continuity, because you can think about as smoothness, and you've been dealing with continuous functions for most of your math career so far. But this is definitely one of the most important lessons. So definitely, if you need anything, watch the recording, email me, do something like that. And then the next class tomorrow will be about derivatives. So this is actually, we will be dealing with instantaneous rates of change, tiny changes, and so on. Okay. So anyone have any final questions?
Will we learn how to find the instantaneous velocity?
Yes, that will be next class. So tomorrow we will be covering that. Yeah. Okay. So if that's it, then I will end the meeting. Thank you all so much for coming. Okay.
Thank you. Bye.
Thank you.
Thank
See
you.
you tomorrow. Bye.
See you tomorrow. Okay. Have a good day.